Hello. Today we are going to learn about matrices. A matrix, the word matrix comes from the Latin word matter, matter meaning matter. Why they came up with this name, we don't know, but a matrix is included in a square bracket. It is rectangular arrangement of numbers, symbols, expressions, and whatever mathematical objects. So, in what we call rows and columns, these are the rows, these are the columns. Right. So, then also the number of rows into number of columns gives you the size. If let us say number of rows is m, then m into n gives the size of this matrix. So this is the first row, this is the second row, this is the third. Similarly, this is the first column, second column, third column. So we call this now, since we have three rows, 1, 2, 3, 1, 2, 3, three columns here, we call this 3 by 3 matrix. Okay? And if, let us say, this is here, m is equal to n, 3, 3. So this is, if m equal to n, this is called what we call the square matrix, because it's in the shape of a square, right? 3 on this side, 3 on this side. Those are the columns of three. And square matrices are very commonly used uh, from a non-commutative ring. Square matrices rather, form a non-commutative ring. Commutative is, you see, uh, AB is equal to BA. Let's say this is commutation, right? A into B equal to B into A, multiplication. So this is non-commutative, meaning A into B is not equal to B into A. That will be non-commutative, right? The very word commutative means actually the product of these two will be same, irrespective of the order, right? So we are done with these two, and then we have just now we talked about ring, right? So the hierarchy is like field, field is a ring is a group. But the other way may not be true. The other way, group may not be a ring may not be a field. So this way it is true. A, a field is a ring is a group. Group may not be a ring may not be a field. We will talk about that in the next class, okay, the next week. Why I just wanted to explain why the square matrix is a non-commutative ring, right? So non-commutative rings, we will learn about rings and fields later. For now, we will stick to matrices only. And the determinant of a square matrix is associated with my matrix. The a square matrix is invertible. Square matrix is invertible if and only if it has a non-zero determinant. If it and only if that is I F if the it has non-zero determinant. Only then square matrix uh, is invertible and eigenvalues of square matrix are roots of a polynomial determinant. Sorry, polynomial determinant. So we will learn about this eigenvalues and the polynomial determinant also down the line. Now, the actual definition of a matrix is it is a rectangular array of numbers. Rectangular m need not be equal to n. Rectangular array of numbers called entries of a matrix. What we go in here are called entries of matrix. And as we have seen, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is basically 3 rows. Here we have 1, 2, 3, 3 rows into 1, 2, 3, 4, 4 columns. This is the size of this matrix is 3 by 4. So these are what is the main purpose of having matrix is the matrices are subject to standard operations like addition, multiplication. Such operations we perform on using matrix in fact. Uh, and there are of course complex matrices. Complex matrices, as you can guess uh, by from the name itself, they are basically uh, made of complex elements, entries. These entries may have complex numbers. And we have already know, these are the rows, these are the columns. So how do we uh, represent the matrix? Now, matrices, as we know, can be the size can be m into n. If m equals n, it's a square matrix. If it has m equal to 1, let's say n equal to can be anything, then we call this the row matrix because it will have while this can have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, that is 3 by 4. That is square matrix. Right? So we will have only 3 by 3, that is square matrix. The second one will be 1, 2, 3. This is, it has only one row and three columns. So we call this the row matrix. Similarly, we can have a matrix 1, 2, 3. This is 1 is 3 into 1. So where n equal to 1, here m, m equal to um, 1 to 3, like some number, and n equal to 1, then we call this column matrix. This is a categorization by the number of rows and columns. Now, how do we represent a matrix? And I mean representation and notation used in matrices. A equal to, as we all know, we use the square braces. A11. This will be A12 and on A1 M, right? M, we have taken M here. Rows are rows are M. So A2 second row, first column, A22 second row, second column, and here we have second row nth. column, you go on like that. M, mth row, mth row, and first column, mth row, and nth column. Right? That is how you can represent matrix. It can as well be included in a ordinary ordinary basis. Even this holds good. A two one to A one one, A one two, A two two, and here A one n, go on A m. This as well, both are valid to represent a matrix. And in other terms also we can represent a matrix. Those are A equal to A equal to ij or square basis also ij. This simply means that A matrix A is made of I rows and j columns, I rows and j columns in both square and ordinary basis. Or you can as well say Aij 1 less than m equal to n. I'm sorry, checking. Yeah, rather less than or equal to m, comma 1 less than or equal to m, meaning from they range from 1 to m, 1 to n. This is another way of representing matrix. Or A equal to Aij I less than or equal to j less than n, meaning n equal to 1. Here we represented it differently. Both can be from 1 to have values ranging from 1 to m, 1 to n. Here both I and j can have the same value of n. That will be n equal to m. Sometimes we also represent a matrix by two bars underneath. This is also a valid form of matrix. So we can represent it this way, this way, this way, this way, this way, this way, or this way. All are all are same, represent same thing. Yeah. Now, uh, sometimes entries of matrix can be defined by a formula. See, A, I, J can be defined by a formula, a function. You can say I, J, then A, I, J is equal to I to J. Meaning, this is not exactly an element, immediate element, but this is in turn, this is a function kind of thing. That function is maps I to J. That's the kind of matrix. You can also have such matrices. Those matrices can also have size m into n, same as ordinary matrices. A kind of example will be uh, I equal to I equal to 1, 2, 3, j equal to 1, 2, 3, 4. Then this will be naturally, this is 3, this is 4, so this will be I j 3 by 2. Now, the set of all n real matrices is denoted by m, n, m, the stylized m, m, or even stylized m, mn, like we denote here. It can be within braces, you can mention after stylized m, and mn, ordinary, this thing, and both belong to the set of real numbers. That's the m by n real matrices in real numbers, basically. Real matrices, the all possible matrices. This, the set of m by n matrices over another field. Let's say if they are over a field, matrices n by n matrices over a field or over a ring. As I told you, a field is a ring is a group. But group mean not the ring mean not the field. So this will be represented by stylized m as usual, m comma n comma r. R here is the ring, or same notation as we call it here, m n into n of r. That is, all possible matrices of a ring, all possible matrices of a field, they can be represented like this, or mm, two, basically two types of notations. If m equal to n, so if m equal to n, what happens? They both will be same, right? Here m and n, m n will be same. In that case, we can write this real matrix, set of real matrices as nr, or even R itself, sorry, n in R itself, or even M or mat represent the set. They represent the set of real matrices over a ring. This is they can be called alternatively M or mat, MAT. Now we go to basic operations. Now basic operations that we can perform over matrices. Addition. Let's say there is a 1, 2, 3, 4, A, one matrix A, B equal to 5, 6, 7. Then A plus B is equal to A plus B. The formula itself is Ij is equal to Aij plus Bij. 1 is less than uh, I less than or equal to n, comma 1 less than or equal to j less than or equal to n. Meaning the values of I can range from 1 to n, the values of j can range from 1 to n. So this is the formula. If you take the above example, a plus b will be 1 plus 5, 2 plus 6, 3 plus 7, 4 plus 8, equal to nothing but 6, 8, 10. This will give you the sum of matrices or the addition of matrices. Scalar multiplication. Scalar multiplication is basically CA ij is equal to C into A ij. Meaning, if this is a scalar, C is scalar here. If you have the product of scalar and a matrix, then you can take out the scalar outside and just put a dot there, that is meaning the multiplication, scalar multiplication of this matrix. So you can separate, bring the C out. Let's say example 1, 2, 3, 4. Here we have 4 into this. This is C is 4 here. So what will this be? It will multiply, this 4 will multiply the whole matrix. 4 into 1, 4 into 2, 4 into 3, 4 into 4 is equal to, of course, 4, 8, 12. multiplication. This will be basically for into this matrix. We call this matrix 4A. This is 4 into. Now, now there is now since we have covered multi addition and scalar multiplication, next thing that comes in naturally is subtraction. Subtraction, if A equal to 1, 2, 3, 4, 5, B equal to 4, 5, 6, 7, rather 8, let's say, then A minus B is equal to, which is, we convert it into addition only, simple addition. This is simple addition of A plus, you multiply, you multiply B with minus 1, multiplication, scalar multiplication. Here, what do you get? A plus minus of B. So, A minus B in the above example will be like 1, 2, 3, 4 plus minus of 1 into 8, 5, 6, 7. It will be nothing but A minus B. So, each uh, element, corresponding element, we go on subtracting 2 minus 5, 3 minus 6, 4 minus 7 is equal to minus 8, minus 7, minus 3, minus 3, minus 3. Yeah, we came up with minus 3, so all three minuses. Okay. So, anyway, so that's the subtraction. Transposition. Next thing. Transposition is denoted by, if A is a matrix, its transpose is denoted by A raised to T. Ij, of course, this is equal to, by definition, A Ji, meaning you are, if you have 1, 2, 3, 4, A equals, A transpose would be 1, 3, 2, 4, meaning you A becomes J, J becomes I. That's a transpose. A transpose. All right, and yeah, uh, matrix multiplication is the most important part. Is matrix multiplication, the maximum basic operations. Now, coming to multiplication matrix, mul- multiplication. We come to this. This is given by if A equal to A11, A12, A21, A22, like that. Let's say A31, A32, A41, A42, A is that one. B is B11, B2, B12, B13, B21, B22, B23, let's say. Then A into B, that is A cross B. Basically, we don't represent it like that. We don't even put the multiplication sign. It means something else. So it can be simply represented as ABIJ. ABIJ will be A1 AI1 B1J and so on. AN IN up to AIN JIN, which is IN. So BNJ, BNJ, and the basic there is called a dot product to differentiate between scalar product. Uh, Scalar product, we have seen scalar product, scalar multiplication. So this is not scalar multiplication. So this is called with a different name called dot product. And the basic condition for a to multiply two matrices is now if A is Mn of size Mn, A and B is Mn, then the rule for multiplication is that B should be of size n into something else, Mn, Np, let's say. So this n of A should be equal to the n, the number of columns should be equal to the number of rows here. This is n is row here. So the number of columns should be equal to the number of first matrix. Let's say if we are multiplying two matrices A and B, uh, A, then the number of rows in second matrix. That is the basic condition. Okay. So now let us say let us take an example. Let us take an example. One, two, three, four, uh, 5, 6, 7, 8. Let's say not even that. Let us say we'll take 9, 10, 9, 10 also. This is 2 by 2 matrix, a square matrix. Right? This is 2 by 3 matrix. Right? So this 2 should be equal to 2 by, I said, those should be equal to the, basically the n should be equal to this starting rows. The columns of this should be equal to, so 2 by 2, 2 by 3. So this is, we can multiply. So then a ij will be 2 by 3 is equal to 1 into 5 here, 1 into 5 plus